This lecture is an introduction to Fourier analysis. Before we can do Fourier analysis, we should be thinking about frequencies and what are frequencies and why they matter. So, why frequencies come up is because they turn up everywhere. Life cycles, seasons, weeks, days, sleep cycles, breathing, heart, neuronal columns, deep brain stimulation, and all these things. But also they turn up in space and in physics all the time. Most things can be described as a rhythmic function. All signals can be broken down into rhythmic functions. And the two most common are the sine wave and the cosine wave. This is the basis of Fourier analysis. Everything can be made up as a repeating signal. It might not repeat very often, but it can still be written like that. And all oscillations or repeating signals can be described by their amplitude, their phase when they onset, and how often they repeat, their frequency. The sine wave is A sine 2 pi, the frequency times time. Yeah. And then the phase. So A is amplitude, frequency is freq, T is time, phase is phase. And so note that sine and cosine are how we describe a circle. We think of sine as this up-down signal like this. But if you're plotting them in the xy plane, you actually get the circle and it repeats around and around. Time is a flat circle. So let's think about frequencies first. This is a 1 Hz sine wave of amplitude 1 over 6 seconds. This is half a Hertz sine wave over 6 seconds. Now, a half a Hertz sine wave means it repeats every 2 seconds. 1 over frequency is time. So here we have a repetition here, and we have a repetition here, and so there's 3 repetitions. Here's a sine wave of 2 Hertz. That means it repeats itself twice in a second. Yeah. So starts here, goes up, goes down, goes up, goes down. Yeah. And so in a 6-second period, we should have 12 peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. And so it looks like that. Now, when we get to higher frequencies, like 100 Hertz, it's very hard to see that's oscillating. It looks like it's constantly there. And that's what we have, for example, with a television or a screen. Screens are changing around 40, 50 times a second, but we don't notice the change because it's faster than what we can see. So that's another way frequencies, while it might not seem like it's oscillating, it actually is. It's just that we're not sampling at the same rate. Then the amplitude. The amplitude just means the height of the wave. So here's a 1 Hertz with 0 phase of amplitude 0.5. Yeah? Just goes up and down between 0.5 minus 0.5. 2 Hertz from 2 to minus 2. 0.1 from 0.1 to minus 0.1. Now, if an amplitude is 0, it means it's not oscillating, but you've considered it. Phase. Phase is important. We don't do a lot of stuff to do with phase in our frequency analysis, but it's good to think about. What does phase mean? Phase means the onset of the movement. When it's phase 0, sine starts at 0. Phase minus pi, or 180, it starts at goes down as opposed to up. So it's out of phase. Minus 180 and plus 180 are the same. And then if you're out of phase by 90 degrees, it's the same as a cosine wave. Yeah. So that's what phase does. It just shifts the alignment of where the wave will start at time 0. Now, phase also matters because if you have loads of things that are on the same frequency but in different phases, and you add them together, as here, you get something that looks flat. That's why phase is so important when you're looking at something. If you don't consider phase, you might say something isn't there, but actually turns out they're just out of phase from each other and it doesn't look like it's there. If things are only slightly out of phase with each other and you add them together, what you do is you get something that's a slightly higher amplitude, but at a different phase. But the frequency is the same. Yeah. And why sine waves and cosine waves are so useful for Fourier analysis is if you add together 3 simple sine waves, so a 1 hertz sine wave, 0.5, a 0.02 sine wave of 1 amplitude, and then a 20 hertz sine wave, you get something that looks quite complicated, even though it's just 3 things added together. The cosine is the exact same as a sine wave. We have amplitude, frequency, time, and phase. But with cosine, we start high, and then we go low and up and down. So that's why the y component is cos, x component is sine. So there are other functions that we consider. We have our square tooth wave, or sawtooth wave, sorry, our square wave, an impulse, or in my own work, a hemodynamic response, which is how blood and oxygen flows through the brain. But these are rhythmic functions that can be described using Fourier analysis. It means you don't have to plot anymore. You can just tell me what frequencies are involved. So, of course, what's the relation between time and frequency? 1 over time is frequency. 1 over frequency is time. So now we get into how we do this. How do we add frequencies together to describe more complicated signals? And we use harmonics. And the harmonic just says is if you have 1 hertz, so that's a 1 hertz, 2 hertz, 3, 4, all the way up to 16. So let's consider this example. What I'm going to do is each of these are slightly different harmonics. And when you add them together, you can get a very different looking frequency. But the thing is, none of these overlap. So they can represent a 1 hertz signal, a 2 hertz signal, 3 hertz signal, and the amplitude of each. If you want to look at more finer detail, you have to use slightly different frequencies. Same with the cosine. 1 hertz, 2 hertz, 3 hertz, down to 16. So now, if I add these together, the sound is like this. That's each one. Do, do, do. But if you play them all together, you get that because they're overlapping on top of each other. Very different sounds for something that's quite pure toned. You can make very complicated sound. And that's the beginning of chords as well in music. But why does this matter to us mathematically? It matters to us mathematically because we can rewrite a square wave as a summation of sines. And the thing that we put in front is amplitude. So what we have is our square wave is equal to summation of sines to infinity in theory. But we'll only look at 31 at the first 15. And what we say is if we add these sine waves together with this different kind of amplitudes, we will get a square wave. So here's our sine wave, our first one. Then we added 2 sine waves. So that's 1 hertz and 2 hertz added together gives us the blue wave. 1 hertz, 2 hertz, and 3 hertz added together gives us this funny looking almost square. And as we keep adding more and more, so 4 sine waves, that's 1 hertz sine wave, 2 hertz sine wave, 3 hertz, all the way up to 4. And then the last one is that's 1 hertz plus 2 hertz plus 3 hertz, but for different amplitudes, and we add them together and we get something that might look like a square wave. Now, why do we use square waves? It's because for testing machines, it's very nice to put in something that has a square wave because it's a very sudden jump into the system. And that's why when you do testing of electronics or things like that, square waves come in. And that's what it looks like for 100 sine waves. Now, it's not perfect. You see here, we have this kind of funny ringing. You have to really get very high because a square wave is square. It's discontinuous. It's very hard to represent using sine waves. And so here we have an animated version of it where we're adding sine waves together to get our square wave look. And this leads us in, this can be extended saying, actually, if we add both sines and causes, we can represent every function as a summation of frequencies. And therefore, we can break things down into a frequency domain. How do we find out the constant, which is the amplitude for each frequency? We have to do some integration. Next class, I'll talk all about the application of this and the implementation of it. It can also be written in this fancier form using ETI NT, but it's the same. So in reality, the mathematics is designed for pencil and paper, and that's what we'll be doing. But it's way too hard. We do very specific examples of it. Most people use something called a fast Fourier transform in computers, and it's much better. Another thing, experimentally, when you're looking at frequencies, you should be very careful about your sample rate. If you're looking for something that's 100 hertz, sample at 200 hertz. If you're looking, if your sample rate is only 100 hertz, you could only think about 50 hertz at most, yeah? Or 512. A lot of machines normally use sampling frequencies that are multiples of 2. So here, I have a sample rate of 100 and my sine wave's frequency 2. I have a sample rate of 100 and my sine wave's frequency 50. I have 25 and we still see it. But now what happens is, if my sine wave is 50 and my sample rate is 100, we don't really see anything. And more importantly, when we go up to, we're looking for something that's 100 hertz and we have a frequency and sample rate of 100, we won't see it. So be very careful about the frequency and sample rate. That's just important for when you're doing projects. And then there's a Nyquist frequency as well, where by mistake you might see a signal that's actually not there. You're sampling within a signal. So the lowest frequency you can look at is how long your recording is. So if your recording is only 1 second, you can only look at 1 second. If your recording is 10 seconds, you can look at 0.1 hertz. So here we have for low frequency, 1 second, 2 hertz, you see the 2 cycles. 1 second, 1 hertz, you see the 1 cycle. 1 second, half a hertz, you only see half a cycle. 1 second, 0.1 hertz, you see this line going up. It has restrictions and has all these issues. How many frequencies can we look at? Once again, that's a choice between how big the signal is and how much sampling you're doing. So to do that, you can do it in Python. You take the signal, you know the sample rate and length of the signal. Very straightforward. But what we get out from it is, this is our signal. That is our fast Fourier transform on the right. And so what we have here is frequency and power. And it's telling us that 50 hertz, it's a power close to 1. Now this is a 50 hertz signal of amplitude 1, so it's not perfect, but that's what we're doing in our classes. We're trying to find out what frequency are we looking for? What power is that frequency? Similarly, if you're looking at it over 3 seconds and only 1/3 of that time is actually working, it'll halve the amplitude. So this matters for the auditory system, but also matters for many other things as well. And sometimes you see a spectrogram, maybe that's more common, where you have frequency here, time here, and color as power. And so what we see here is there's no power in the 50 hertz before 1 second, then there's loads of power, and then there's no power after. So this might be a better way of representing it. Another way of looking at it is like this. We see speech and we see all the frequency bands. It's a very nice way of representing speech in terms of frequency bands. But once again, you'll see this for space. You'll see this for every different kind of signal. So a note is Fourier transform, Fourier series, just use sine and cosine waves. There are other methods using more advanced looking waves, but it's all the same logic, and they're called wavelet analysis. In the next lecture, I'll implement the Fourier analysis to analyze a signal.